Hey math students! Today we are reviewing the concepts of domain and range. Before we get into our definitions and examples, we'll start off with a warm-up. So go ahead, pause me, give these problems a try, and then we'll come back together and review it. Welcome back. So in this problem we have Daria, and when she was born she was 18 inches long. Then between the ages of 0 and 10 years old, Daria grew 4.5 inches per year. So there are a bunch of different ways to solve this problem. I'm very analytical, so I'm going to solve this by creating a function. And the function that I'm going to make is h of t, where h represents Daria's height, and then t represents time in years. You maybe did this problem in your head or drew a picture. I'm going to make a function, and a function is helpful because you won't always be able to do these problems in your head, and it's good to know how to construct a function. So if she started off 18 inches long, that's like our starting point, so 18, and then every year she grew 4.5 inches. So that is like our slope. So 18 plus 4.5t can be our function h of t. So when she's 3 years old, this is represented by h of 3. So I just have this. I've got to do some math in my head. So 4.5 times 3 is 15.5, which is 33.5 inches. That's pretty short. I don't know if this is an accurate problem, but I don't know. Okay, so 33.5. And then at what age was Daria 50 inches tall? So now we're looking for when is h of t equal to 50. So I'll set those equal. 18 plus 4.5 equals 50. I don't know if I'm prepared to do this math. I should have done it beforehand. Oops, I forgot my t. My t is right there. So subtracting 18 from both sides, I get 32. So I'm just going to leave this as a fraction. Now I'll divide by 4.5, and I get t equals 32 divided by 4.5, like that. I could plug it into a calculator, but I won't. So a relation is just a set of ordered pairs. So ordered pairs, in case you don't know this word, ordered pairs are coordinates. Like an x and a y coordinate. That's an ordered pair. So a relation is just a bunch of ordered pairs that you can plot. Okay? So you can see on the right we have that relation that is 5 ordered pairs, or 5 coordinate points. And then the domain is the set of all x coordinates of the ordered pairs of a relation, the set of numbers that are the possible inputs. So in the case that we have to the right, the domain are the possible inputs. I'm going to write them all out. So I'm just going to look at all my x values for the domain. And if you really need color coding, I'll color code it for you. So I'll highlight these in blue. There they are. Those are my possible inputs. So I have -2, 0, 1, and 4. I don't have to write 1 twice. I just write it the one time, even though it appeared twice. Then the range are the set of all y coordinates of the ordered pairs of a relation. So all the y coordinates. This is the set of all possible outputs. So I'll do my outputs in red. Oopsies. Red. These are my output values. So, oops, I forgot to highlight. here. Which are 3, -1, 2, -3, and 0. That's my range. And then at the bottom, we just have multiple representations of what these could look like. So my x, I'm just going to put my coordinates into the table of values. I don't know if you've done mapping in a while. We're not going to do this too much in the class, but it's going to help me know whether these are a function. So here is a big definition. Function is a relation in which each value of the domain is paired with exactly one value of the range. So you may have heard this before as only one output for every input, or that it needs to pass the vertical line test. Okay, these are some little quick definitions that you may have heard in the past. So mapping and graphing kind of helps us figure out if this is a function or not. So when I map, I'm going to list all my domain values over here and my range values over here. So I'll just use the domain and range I found. And I'm going to put these from smallest to biggest. So smallest goes -2, 0, 1, and 4. And then the range from smallest to biggest is -3, -1, 0, 2, and 3. Okay. So then when I map, I kind of connect the dots. So I know -2 goes to 3, 0 goes to -1, 1 goes to 2, and then 1 goes to -3, and then 4 goes to 0. So I'm going to be looking at this definition. Is there only one output for every input? No. So for this input 1, it goes to 2 outputs. And if you don't really understand the mapping, we could also graph it. So I could also plot these points. I'm going to zoom in on my graph to make it easier to plot. So I have -2, 3, which is right here. I have 0, -1, I have 1, 2, and I have 1, -3, and then I have 4, 0. So when I graph, it's easier for me to check if it passes the vertical line test. And if I take this ruler out to check the vertical line test and see if it passes, I can see that right here at 2, it does not pass the vertical line test. If I were to draw a vertical line through the x value 1, it does not pass that vertical line because it passes through 2 points. So I can see based on the mapping and the graph that this is not a function. No. So these are two really different graphs. One is a parabola that you can see kind of goes forever here. Whenever you see a function go off the graph like that, just assume that it's going forever. So you can always draw arrows at the end of graphs like that. Okay? So that's going on forever. And so when I find the domain is all x values because I know it's just going on forever and ever. And then the red range are just the y values less than or equal to 2, because it still goes all the way up to 2 right there. Okay. And then the graph on the right is a little different. It's a little bit more abnormal because you can see that there's those endpoints. And I want to kind of remind you that some endpoints are open circles, which means it doesn't include the value. So I'll make a note. open circles do not include the point. And then right here we have a closed circle. Closed circles do include the point. Oops. Okay. But basically, interval notation uses parentheses or brackets instead of the inequality signs. I know this is a lot of notation, but if this is new to you and you don't really understand it, I do recommend writing it all down, just because it takes practice. So I want to note, some students aren't aware of this, when you have infinity, so infinity, so plus or minus infinity, always uses parentheses. Oops. Always uses parentheses. Like this. And that's because infinity isn't a real number. It's just kind of like a really, really big number that's keeps going and going and going. So it's not a real number. So I do want you to practice this. And one thing that I want you to try to do as you're copying down these notes is I want you to shade in the number line representation properly. So I'll show you what I mean. I want you, so if I have this notation that the domain is between A and B, or X is less than or equal to A, or less than or equal to B and greater than or equal to A, I would need to shade in on the number line what that represents. So I have my closed circles and I would shade in between those. Okay, and then the same thing down here, very similar, except I have my open circles because I see I have parentheses and I have not equal to inequalities. So I want you, as you're copying down these notes, to also shade in properly on the number line, just to test, to make sure you understand what these inequalities mean. So you're shading in what are the possible values for X. Pause me, then we'll come back and I'll show you what the shading looks like. Okay, so here's how you should have filled in the number line representations, shading what the possible values are for X. Hopefully, if you're more familiar with inequality notation, you can become more comfortable with the intervals using parentheses and brackets. Alright, let's do some examples. So for each of these, we need to determine the domain and range of the relations, and then, oops, I forgot a word, we need to determine if it is a function. So this graph A, I see that I have a closed circle on the left and an open circle on the right. So that means I'll have a bracket and then a parentheses. And so the smallest value of X, because domain goes, it's how wide it is, left and right, is -5. And the biggest X value is 5. And then the range, the smallest, well, I see that we have the smallest value is a closed circle at -2. And then the highest Y value, I know it's like not very clear. Let's say it goes all the way up to that 7. So there's a point here. That's the highest value at 7, and I will use another bracket because you're basically anywhere where the graph goes, we could draw a point, right? Is this a function? So is there only one output for every input? If you like to use the vertical line test, I'll bust out my ruler again so you can see, does it pass through this vertical line twice? No, just once. This is indeed a function. Domain from a table. This is where we're gonna wow, that was hideous. This is where we're gonna use the notation like we did on this first page for the domain and range, where we just list the points. So it looks like, there it is. Okay, so the domain are the x values. So I have 2, -1, -2, and then another -1 and another 2. Okay, so I don't have to write them down because they repeat. And then the range, I have -2, -1, 0, 1, and 2. Oops. I'm going to use my curly Q brackets. They're kind of hard for me to do, I guess. Alright, so then I need to determine, is this a function? And I can see right here that the value of 2, if I were to map these out, 2 maps onto both -2 and +2, and then -1 maps onto both -1 and +1. So because I have inputs that match with multiple outputs, this is not a function because of what happened there. And then part C. So this is kind of going off the page, but there is an arrow here. When it goes off the page and doesn't make it clear, you can just think that it's an arrow. So the domain are all the possible x values. So I see that I have arrows at the end going left and right. So this goes from -infinity to +infinity. And I'll use parentheses because you always use parentheses with infinity. And then the range, the smallest y value is down here. And we'll say that is at 3. I'm going to use a parentheses because it's an open circle. And then the arrow keeps going up, so the y values keep going to infinity. Is this a function? What do you think? Here's my ruler. What do you think? Does this pass the vertical line test? Right here's the tricky part. Is that 1 input or 2? That's just 1. So we have the closed circle and then the open circle. So the only point is the higher point up there. And yeah, this passes the vertical line test. This is a function. So draw a function that has the following domain and range. And there are so many different possibilities for what this could look like. I kind of feel bad showing you what my answer looks like, just because your answer could look totally different than this, and that is okay. I see that the domain goes from -1 to 3, and then the range goes from -2 to 4. So I don't really know what it looks like between these points, but I can do a little guess. I'll do it in red. So I'll draw a point at an open circle at -1. I want to make sure it goes all the way up to 4. It touches 4, and it goes all the way down to -2, and then keeps going to 3, and then has a closed circle because of that bracket. So I know that my function can't go any lower than -2 or above 4. It has to stay between those points. So here's a possible solution, and it is a function because what I drew does pass the vertical line test. Okay. I want you to try the next one on your own. So I'll start drawing and you start drawing. And I want you to look down at your own paper and try this on your own. Don't worry about what I'm doing. Here's mine. Yours could look different. So I just made sure that my x values went all the way to -infinity. You see the arrow at the end, and then stopped at +3. And then the range, the lowest y value is -2. Actually, mine needs to go, it looks like a little lower. There it goes. The lowest y value is -2, and then it goes up to positive infinity. That's mine. Yours could have been different. And that is the fun of math.